I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where we are answering the question why infinity divided by infinity is considered indeterminate. You can look here at this starting example. Notice infinity divided by infinity represents a quotient, so we are looking at rational functions. X divided by x, limit as x approaches infinity. Independently, the numerator and the denominator functions arrive at infinity. Independently they do, but when you evaluate this limit, you know you're looking here at limit as x approaches infinity. I have a 1. I have a same function divided by the same function, it's equal to 1, so I'm evaluating a horizontal line. As x approaches infinity, my output should be 1. So here we really have a form infinity divided by infinity, but we end up seeing an end result of 1. Let's look at another example. How about this? Limit as x approaches infinity, I have x squared minus 10 divided by x squared plus 20. Independently, the numerator and the denominator functions arrive at infinity. If you put infinity in the numerator, it's arriving at infinity. In the denominator, the same. As you saw in this example, and as you see here, relatively, here the rate of arrival at infinity is exactly the same in the numerator and denominator because the functions are the same. Here the rate of arriving at infinity, the rate of change of the function, is reasonably similar, or perhaps one can even say it is similar. The derivative of x squared minus 10 would be 2x. The derivative of this is 2x. You have identical rates of change, so therefore they're arriving at infinity at the same time. When you evaluate this limit, and it's a rational function, you can do x squared minus 10 divided by x squared divided by x squared plus 20 over x squared. You have here 1 minus 10 divided by x squared divided by 1 plus 20 over x squared. Limit as x approaches infinity, these zero out. I have here a 1 over 1, and my end result here is again a 1. Look here at this example now. Limit as x were to approach infinity, I have different functions, hyperbolic cosine and hyperbolic sine. Now when you evaluate these, the rates of change of both of these functions arriving at infinity is reasonably the same. When you graph them out, you have a hyperbolic cosine which looks something like this, and you have the hyperbolic sine which looks something like this. As x approaches infinity, both of these are arriving at infinity at the same rate, relatively at the same rate. So when you do this limit evaluation, you can break them down into their functions. You'll have e to the x plus e to the minus x divided by e to the x minus e to the minus x. Evaluate this, you'll end up seeing you'll have 1 over 1 again, and it'll be a 1. If you do a common denominator, you'll end up seeing you have e to the power of 2x plus 1 divided by e to the power of 2x minus 1. And then you can divide everything by e to the 2x, and you'll end up with 1 over 1. Again, you're seeing here the limit, even though the functions are independent and they're different, they're arriving at infinity independently. They're arriving at the same rate, so we end up seeing a value of 1. So up till now, all the examples I've shown you, here I'm seeing infinity divided by infinity is equal to 1, but that's not always the case. Look at this example. Limit as x approaches infinity, I have e to the x divided by natural log x. When you evaluate this in terms of a graph, exponential function looks like this, the natural log looks like this. As x is approaching infinity, exponential is arriving at infinity much faster than the natural log. Here's your exponential, here's your natural log. The derivative of this is e to the x, the derivative of this 1 over x. The rate of change of exponential is much faster than the rate of change of natural log. So you know you're looking at something which is arriving at infinity in the numerator much faster than the denominator. Both of these independently are eventually arriving at infinity, but this is arriving much sooner, so your end result for this limit is positive infinity. Now we're seeing an infinity divided by infinity is giving us a positive infinity. And there are other examples which would confirm this as well. You even have this example. Limit as x approaches infinity, I have hyperbolic cosine x divided by x. Independently, both of these functions arrive at infinity. So we have an infinity over infinity. But the rate of change of this numerator is much faster than the rate of change. The rate of change of this is a hyperbolic sine. The rate of change of this is a 1. This is a much higher rate of change. As x approaches infinity, this is arriving at infinity much sooner than this. So you're seeing here again you'll have a positive infinity output. Now let's look at something slightly different. I have limit as x approaches infinity root x divided by exponential. When I graph these, the exponential looks like this, the root x looks like that. It doesn't have to be exactly accurate, but we are looking in the direction of positive infinity. The exponential has a much higher rate of change than the root x. The derivative of this e to the x, the derivative of this 1 over 2 root x. This is a much higher rate of change than the root x. So we know over here with the exponential now sitting in the denominator and each of these independently arriving at infinity, what we are seeing is a higher rate of change in the denominator, a smaller rate of change in the numerator, and we'll zero out. What we will end up seeing is we're really looking at kind of 1 over infinity or something over infinity, and it's going to zero out. So now we're seeing an output over here to be 0. We close with this last example. Limit as x approaches infinity, I have root x divided by x cubed. You know you have two functions which independently arrive at infinity as x approaches infinity, because if you graph them out, they do. Here's root x, it will eventually hit infinity in terms of your range, and x cubed, we can show it like this. It will eventually hit infinity as x approaches infinity, but you know the rate of change of this is much higher. It's 3x squared. The rate of change of this is 1 over 2 root x. This is arriving here much faster at infinity than this. So what we will see is we will zero out again as well, because the denominator value rate of change will be much higher than the numerator. It will zero out. So now we're saying infinity divided by infinity shows us a value of 1 sometimes it's infinity, sometimes it's 0. But this ambiguity we see and the lack of a consistent result, we're not consistently arriving at a single result, we're arriving consistently at different results. Therefore, infinity divided by infinity must be nothing other than indeterminate. It all depends on the type of functions, and it depends also on the rate of change of those functions and the behavior of those functions as x approaches infinity. Some functions arrive at the same rate, some functions arrive slower, some functions arrive faster, and hence you see these varied results. Infinity divided by infinity is nothing other than indeterminate. Thank you for watching.